Welcome to the Components of Internet of Things course.
Hello and welcome to this course on components and applications of Internet of Things. This introductory part will cover some basic definitions, motivation and use cases. And then over time we will get into more depth. First segment will also give you a sense of what this course will look like. In this lecture, a high-level overview of Internet of Things and application is covered. Decades ago, we connected computers and got today's powerful internet. We will have we have started to connect everyday objects using internet to create Internet of Things. You have probably heard that world will have 50 billion connected devices by 2020. As these devices come online, the industry will face some challenges such as ensuring the security of its devices, powering billions of sensors, and analyzing the data generated by these devices. Therefore, it is important to look at the underlying components and the entire ecosystem integration issues and applications. First of all, let us ask, why do we think of Internet of Things and what is it? If you look at the basic definition, Internet of Things is the network of physical objects such as devices, vehicles, buildings, and other items embedded with electronics, software, sensors, and network connectivity that enables these objects to collect and exchange data. There are other definitions also. If you look at the basic Wikipedia, then you'll see Internet of Things is also called Internet of Objects, refers to a wireless network between objects. Usually the network will be wireless, self-configuring, such as household appliances. If you look at WC's definition, WC's World Summit on Information Society, it's a pair conference about information society. Its definition goes like this: by embedding short-range mobile transceivers into a wide array of additional gadgets, everyday items, enabling new forms of communication between people and things, and between things themselves. Or if you look at the ITU definition, it is a global infrastructure for information society, enabling advanced services by interconnecting physical and virtual. The interconnection could be physical and virtual, interconnecting things based on existing and evolving interoperable ICTs. According to ITU, there are basic characteristics for this IoT: interconnectivity, things related services, heterogeneity and dynamic changes, and it is in enormous scale. So what exactly the interconnectivity we mean? Interconnectivity related to interconnectivity is regards to the and regards to the IoT is anything can be connected with the global information and communication infrastructure. Things related services, the second characteristic, the things related services. The IoT is capable of providing things related services within the constraints of things in order to provide thing related services within the constraints of things. Both technologies in physical world and the information world. The heterogeneity characteristic says that devices in the IoT are heterogeneous as based on different hardware platforms and networks, and they can interact with other devices or services or platform through different networks. The dynamic changes is also very important. The state of the devices change dynamically. That means, for example, the devices will be sleeping, waking up, connected or disconnected, as well as the context of the devices, including location and speed, can change. Moreover, the number of devices can change dynamically. But the fourth or the last point is it is an enormous scale. The number of devices that need to be managed and that communicate with each other will be at least an order of magnitude larger than the devices connected to the current internet. The ratio of communication triggered by these devices as compared to communication triggered by human will noticeably shift towards device triggered communication. Even more critical will be the management of the data generated and their interpretation for the application purpose. This related to semantics of data as well as efficient data handling. So if you look at the various names and you can see everything conveys the same concept, whether it is machine to machine communication, internet, everything, world size web, Skynet, etc. So everything meant to means the same. British entrepreneur Kevin Ashton first coined the term in 1999 while working in Auto ID Labs, originally called the Auto ID Centers, referring to a global network of radio frequency identification connected objects. Typically, IoT is expected to offer advanced connectivity of devices and systems and services that goes beyond machine-to-machine communications and covers a variety of protocols and domains and applications. Interconnection of these embedded devices, including smart objects, is expected to boost the automation in every field while also enabling advanced applications like smart grid or expanding the area such as smart cities. So that's a brief history of Internet of Things. Let's look at the brief history of Internet of Things. The term Internet of Things is 16 to 18 years old, but the actual idea of connected devices had been around longer, at least since 1970s. Back then, the idea was often called embedded internet or pervasive computing. But the actual term Internet of Things was coined by Kevin Ashton in 1999 during his work at Procter and Gamble. Ashton, who was working in supply chains optimization, wanted to attract senior management attention to a new exciting technology called RFID, because internet was very hot that time, new trend in 1999, because it somehow made sense. So he called his presentation as Internet of Things. Even though Kevin grabbed the interest of some Procter and Gamble executives, the term Internet of Things did not get widespread attention for the next 10 years from 1999 to 2009. The concept of IoT started to gain popularity in the year 2008 to 2010. So in those days, 1999, the internet was concept was anytime, any place communication, anytime in the sense daytime or night, outdoor or indoor, or on the move, or any place in the sense again at the PC, indoors, away from the PC, outdoors or on the move. Then a third dimension was introduced, or like we have shown in this picture. So we have two dimension, anytime connection and any place connection, and we have the third dimension, anything connection between PCs, human to human, or sometimes called H to H, not using PC, or human to thing, H to T, using a generic equipment, or a thing to thing, T to T. So the third dimension is very relevant to Internet of Things, where anything connection is possible. So apart from any time, any place connection, we have anything can be connected to the. So that gives you some perspective of Internet of Things. So if you look at, we have around 1 billion smartphones, or 1.8 billion computers, or 4.5 billion traditional wired or wireless phones. This data is taken from Data Summit 2015, and roughly we have around 7.2 billion inhabitants of the earth. Tomorrow we are expected to have 8.5 to 10 billion inhabitants of the earth, 12 to 30 billion wearable devices, and 50 to 150 network devices, 150 billion network devices, or 50 to 100, 10 to 10 to the power of 12 identifiable objects, or 2000 to 1000 to 10 to the power of 21 bytes or zettabytes of cloud traffic per year is expected. So that's the scale of things we are talking. Or in 2010, if we had only very few devices connected to the net, like a smart fridge or automobile with some sensors, or as we commute from home to workplace or workplace home, we were able to control uh, some devices. But if you look at now, a lot more devices or application has been in the in the market, as well as new ones is on the way. So here we can see that as we move from home to workplace or workplace to home, most of the devices we can control from using this concept, including your room heating or lighting or washing, etc., can be controlled. That's one of the use case. So what is expected predicted growth? In the beginning I said by 2020 we are expecting around 150 billion. By 2020 we have 50 billion devices connected to the net. The y-axis shows the billions of devices, and x-axis shows the time. So as we go, since the inception in 2009, you can see there is an exponential growth in the number of devices connected, and it will exceed 50 billion by 2020. This is the data from Cisco, the company Cisco, which is this data is taken from 2015. So we are expecting more or less the same trend. So if you ask where is IoT, the simple answer is it is everywhere. Also, it is important to uh, understand the difference between what do you mean by an intelligent device or a smart device. An intelligent device is any type of equipment or instrument or a machine that has its own computing capability. Simply we uh, define any intelligent device is a type of equipment or instrument or a machine that has its own computing capability. So a smart machine or smart device means a smart device is an electronic device generally connected to the other device or network via different protocols. Then we usually we refer to as a smart device. Of course, it has its own computing power. So if you ask why Internet of Things, uh, there are many factors. The dynamic we are talking about smart factories, dynamic control of things, or dynamic control of industry and our daily life. Energy conservation is a prerequisite for the Internet of Things. Therefore, research producing new knowledge on how to develop more energy efficient electronics will influence design of all electronics. The concept of energy harvesting will enable larger and larger portions of the consumer energy market to be generated by the ambient renewable resources locally, and thus reducing the losses in the long distance energy distribution. For example, a similar effects will be experienced in road transport and cars. Already today, there are hybrid cars available harvesting kinetic energy to drive. This is in combination with the better and more environmentally friendly energy storage in the future will make electrical devices achieve more longer range and become more attractive alternative. The abundant sensory information will enable unprecedented energy optimization and control, or more energy optimized control. Climate control is the most energy consuming activity in modern buildings. House could adjust room temperature according to the person's preferences of those room of those in the room, and avoid heating and cooling of rooms excessively without benefits to the inhabitants. So these concepts or this dynamic control will improve the overall resource utilization and better relationship between human and the nature by by using more and more renewables, forming an intellectual entity by integrating human society and physical systems. So that is a that's why we are after Internet of Things. One of the basic driving force for Internet of Things, we have to look at the computing power. Why so much? What is the main driving force that enables Internet of Things? There are three fundamental three laws which drives Internet of Things. That is Moore's law, Metcalfe's law, and Kumi's law. Moore's law is the observation that the number of transistors in a dense integrated circuit doubles approximately every 2 years. Metcalfe's law states that the value of telecommunication network is proportional to the square of the number of connected users to the system. And Kumi's law describes a long-term trend in the history of computing hardware. The number of computational per it says the number of computations per joule of energy dissipated has been doubling approximately every 1.5 years. So the number of computations per joule of energy dissipated has been doubling approximately every 1.5 years. So we look at Moore's law and Metcalfe's law in little detail, and more importantly, what can you do by combining and analyzing the signal from all these IoT devices, that also we need to discuss. So if you before we go into more uh, Moore's law's definition, Moore's law's prediction, we should look at generations of computers. The first generation was 1940 to 1956, we call vacuum tube era. Second generation 1956 to 1963, where transistor era. Third generation, where we have the integrated circuits 1964 to 1971. Fourth generation 1971 to the present day time, where there are microprocessors, and we have fifth generation from present to beyond, where we call it artificial intelligence era. If we consider the fourth generation of microprocessors, so here we have shown a small subset of processes, right, starting from 1.5 micron technology. So 1.5 micron here, it means that the size of the transistor which implement the basic switches. So 1.5 micron to 0.13 micron. So what is shown in this picture is each and every generation of different generation of microprocessors that is present in the IC or the chip. So the Moore's law states that the number of transistors that can be integrated doubles every 18 months. So that means today, if we have uh, 1 billion transistors in this area, in this square, in 2 years from now or 18 months from now, we can integrate the same number of transistors in this much more smaller area, or this much area. So another way of saying is that given an area, the number of transistors, let's say it is 1 billion, in 18 months time, uh, we can, using the same area, we can integrate 2 billion transistors. So integration capacity doubles every 18 months, and this trend has been continuing. So if you look at the x-axis shows the year and y-axis shows the number of transistors. So this is kind of a semi-log. This is a semi-log plot. So that's why the graph becomes linear in this picture. So, for example, if you go from 1997 to 1999, you can see almost the number of transistors have doubled. So that trend has been continuing in all the market, including desktop, embedded GPU, or server market, and the general trend is continuing in all areas of this computing. So this is a sample of 129 microprocessor chips in the market, and Moore's prediction was exactly the same trend was continuing last 50 years. So what does it mean? What does Moore's law has meant? If you look at a Cray machine in 1976 with 250 million operations per second, 170,000 chips, half a billion transistors, and 500 kilogram of weight, and it costed around $9 million, and only 80 Cray machines were ever manufactured. Whereas if you look at 2017 iPhone market, there are 10 billion operations per second. We can do a 10 billion operations. There are 16 chips inside the uh, iPhone, and 4.3 billion transistors that include only the CPU, and it was weighing only 174 grams, so it's less than 5 watt it was consuming only 5 watt power and it costed only uh, $999 or less than $1,000, and 3 million iPhones were sold in just 3 days. So that is a scale of, we are talking about from 1976 to 2017. So if you look at another view, what Moore's law has meant, so we have 12 generations of iPhone since 2007. So you can see 10 generations, right from iOS version iOS 1.0 to 11.0.1. So there are multiple uh, versions in the same year. So Metcalfe's law says that the power or a power of a network increases in proportion to the square of the number of nodes on the network. Suppose you have 2 computers, so we have only 1 connection. If you have 3 computers, we have 3 connections, or 4 computers, we have 6 connections. 5 computers means 10 connection. That means 5C2 is 10. 10 computers are 45 connections, and 12 computers means 66 connections. So as the number of computers increases, the connectivity grows, and the power of the network increases in proportion to the square of the number of nodes. So how about the 20 connections? The picture may look like this, and the power of the network is huge. The number of connectivity is too much. Is if you have 100 connections, almost 5,000 connections. So the more that join the internet, the more useful the internet become exponentially. The network internet become more useful as we connect more and more devices. Imagine what a billion net connection look like. So the disruptive force is enabling Internet of Things. These are some of the factors: Moore's law, Metcalfe's law, Kumi's law, and uh, that is the main driving force. The computing power, that is the number of computation that you can do per chip has increased exponentially. More transistors will allow wireless communication in every device. So the moment you have more compute power in devices, we have more communications also possible. We can integrate all the stack of communication into these small micro chips, and anytime, anywhere connection, any object connection is possible. And another law that is close to IoT is the Bell's law. A new computer class emerged roughly every decade. So here the graph, we have x-axis is the years 1950 to 2020, and people per computer. So in 1950 we have a mainframe, one mainframe computer per enterprise, and later on we have one mini computer per company, and around 1965 we have one workstation per engineer. If you go one more decade down, we will see one personal computer per family, and if you go one more decade down, we'll see one laptop per professional, and if you go one more decade, one smartphone per person. If you will one more decade down, you'll see smart sensors, but in this case, uh, not one but hundreds of sensors per person. That is a huge change in this decade. So when we are talking about IoT, we have talking about large number of sensors per person or so what IoT can do through the exploitation of identification and data capture, processing, communication capability, IoT makes of useful full of things to offer services to all kind of applications while ensuring that the security and privacy requirements are fulfilled. So we have the data capture and to from various sensors and analyze this data and communicate it between devices, and we can take appropriate or intelligent decisions. The following graphics from Become Research depicts how the Internet of Things may interact with various service sectors within public and private sectors and ordinary consumers. Public sectors, entities such as universities, may have some level of involvement and interaction within the service sectors depicted. So we have devices, locations, applications, application groups, and service sectors. So ranging from operation and industry elements of buildings to levels of research and retail entities, transportation, IT networks, all the sectors interact. That is the main message from this graphic picture. Devices, location, application groups, and service sectors, whether public and private, interact uh, in using this new technology. Now, let us look at some of the basic applications. Let's look at a smart home applications where maintaining a comfortable temperature and heating of water are the most energy consuming tasks of the house with huge potential of energy conservation. If we can cleverly control the heating and uh, the water resources as a huge potential for energy conservation. As a consequence, a significant positive impact on the environment. This is further discussed later in the course when we discuss about smart home applications. These devices will collaborate autonomously with the house sensors, and the control of various things become much more easy. The intelligent appliances will collaborate to conserve energy and to signal a need for a new supplies of food, detergent, maintenance, etc. Some of which may be satisfied automatically by the corresponding sensors. This will take this will take away some of the today's tedious housekeeping applications if you have a smart house. Or it could be a smart egg tray where this is a product that is currently available in the market. An egg minder features basically it's a built-in Wi-Fi chip to allow to sync up with the smart device via an application or app. Once paired with your smartphone, the tablet, you can now open up an app from anywhere to view how many eggs you have, which will help you in the grocery or in the shopping, or you simply just don't think to check on your egg count head before heading outdoor. Egg monitor can still do more in the actual egg crate. Next to each egg, an LED light that will alert you which egg in the bunch is oldest and should be used quickly before it is getting damaged. So the before things get, so the older ones should be used faster. Or it could be a smart washing machine where uh, you can delay the actual we are talking about a smart energy usage, where if you wash the machine cloth at a specific hours, the energy cost will be minimum, so you can cleverly control from your smart device the washing process. Or it could be a smart sleep system to visualize your sleep cycles, understand what wakes you up, and compare your nights from your smart app that you can control your personalized wake up and sleeping periods. Or it could be a smart weather station which controls your temperature inside the room, the humidity inside the room, and give you a healthier home. Or your cooking application. So these are the some of the products that is already available in the market, which will be already that is available in the market. Or it could be a smart garbage can and alert the authorities when it is full. So these are the companies that is already giving these IoT applications currently in the market. Or smart water is an important resource, and supply monitoring is going to change with IoT everywhere. I just want to give you a sense of how extensive it is, the application side. In fact, you save a lot of water by clever monitoring, cleverly monitored gardening. Pretty much anything you use, anything you see, you might want to ask yourself, will it will that go on an IoT? So large number of or n number of applications can be thought of using this technology. Or if you look at the transportation, under IoT regime, traffic could change, or the traffic management will change. We could track emissions. When there is a queue, the first car may tell the cars behind there is an accident or just too much traffic. That's why the traffic is going slow. And there will be eventually make intelligent navigation system replan your route of cars and program to go down already saturated, avoid saturated roads. The cars may help driver to keep safe distance to the car in front, or may refuse dangerous actions like speeding if weather conditions are unsafe, or overtaking if the oncoming cars goes too fast. These cars can go autopilot on highways, reducing the risk of fatigue-related accidents. And you could see applications on and on. The list can go on and on. Or a company with a large number of uh, vehicles, fleet of vehicles, can collect or monitor their activity, location, vehicle metrics, driver behavior, or the miles currently hours, miles driven, etc., and transmit the data to a data center, and using some of the data mining techniques, the web, using web or mobile device accessible, you can access the overall uh, data or reports. That way very easy to control or manage the transportation facility or for the company. It will be very easy. So if you look at the IoT segment, you can see at the moment this is some quarter 2016 quarter 3 results from IoT analytics. The connected industry takes around 22%. Smart city market is around 20%. Smart energy is 13%. Connected cars 13%, and others 8%. So there are also large number of applications in agriculture, connected buildings, connected health, smart retail, and smart supply chain. So huge potential for in all these segments. So in the later part of the course, we will discuss various IoT architectures. So in the bottom layer, we have sensing and identification. Then we have the network construction, information processing, and integrated applications. So these segments we will discuss later on. One thing I also want to clarify is that there is a subtle difference between Internet of Things and connected things. Connected thing is when things are connected to each other, but they may not be connected to the internet. Internet of Things has been things that also are connected to the internet. So when I say connected, need not be connected always. For example, there can be a local connection between all the sensors in a car. There are 200 sensors in a car, for instance. How do we implement a thing? Uh, there are many different types of microcomputers available to implement smart objects. So we will look at later on how do we implement a smart thing. Arduino Uno or Raspberry Pi or a BeagleBone Black or an Intel Galileo. There are various types of microcomputers available to implement smart objects. They are small, cheap, and flexible computer hardware that allow end user programming become an end user programming to become an IoT object. For example, Raspberry Pi is a fully customizable and programmable smart computer board, which similarly we have other uh, microcomputers available in the market. Sensors and actuators play an important role. The ability to detect changes and control in the physical status of the things is essential for recording changes in the environment. Sensors and actuators play an important role in overall application development. So we will look at the various sensors and actuators, right from a clever machine vision application to whether it's acceleration, magnetic. There are different sensors and actuators available in the market. So we will cover this in the later part of the course. There are also a large number of sensors available in the market, right from different colored LEDs, relays, microphones, small microphone, joystick, digital temperature, analog hall, etc. So depending upon the application, we have to choose the right sensors and actuators. Wireless LAN technology plays an important role. Wireless sensor technology a pivotal role bridging the gap between physical and virtual worlds and enabling things to respond to changes in their physical environment. The the ratio of communication triggered by devices as compared to communication triggered by human will noticeably shift towards device triggered communication as things are, as I said before. For example, uh, there will be more and more even machine triggered communication compared to a human triggered. Sensors in an electronic jacket, for instance, can collect information about changes in the external temperature, and parameters of the jack can be adjusted accordingly. So all these clever things are wired, connected wirelessly. So wireless technology plays an important role depending upon the proximity. Sensors such as RFID or wireless personal area network, which is, so typically the classification is based on the range of uh, the distance range, short range, medium range, or short medium range, or long range, and each of the verticals we have separate technology depending upon how much energy they consume, depending on the protocol used and the data rate. So we will look at each of these wireless technologies later on in later part of the course. So there are many challenges in the IoT space. Uh, Technological standardization in most areas still remain fragmented. One major barrier for the widespread adoption of Internet of Things technology is the absence of governance. Without an impartial government authority, it will be possible to have a truly global Internet of Things accepted by states, companies, and trade organizations and common people. Today, there is not a unique universal numbering scheme. So, a lot of standardization needs to happen. There is also the need for keeping governance as generic as possible, as having one authority per application field will certainly lead to an overlap, confusion, and competition between standards. Objects can have different identities in different contexts, so having multiple authorities would create a kind of multi-homing, which can lead to disastrous results. Connectivity still is a problem. So a lot of works needs to be done in better connectivity, and the power management, powering those sensors is also a big issue. And security, to some extent, is just like a security of the web-based system, but it is different because underlying protocols will be different. There is a just tendency to just feel we need to connect everything, and when we have connected everything, then we will be able to run the right sort of massively powerful software, and everything will work. There is a danger there, however. So from the security point of view, right now the only reason that internet really works for computers is because it is getting updated. So we can provide the right update for different security reason, but that may not be possible in all cases where if they are not properly wired or connected to the system. The number of devices that needs to be managed and communicated with each other, at least in order of magnitude larger than the device connected to the current internet. So the large number of devices, then the security also become an issue. So things are quite rapidly changing. So also we need multiple expertise in system perspective and control and software. So all these areas, so this application crosses interdisciplinary boundaries. So we have system engineer and the control engineer and software expert all needs to work together to make something work. So the interdisciplinary boundaries needs to be realigned, new fundamentals needs to be created, and new technologies and tools needs to be developed, and education needs to be restructured, because we have a large variety of uh, applications, and the right platform needs to be developed for the fast development of various applications. Also, uh, sensors collect data from various environments and generating information and raising awareness about the context, or the getting data or information from the data. We need to have large amount of processing needs to be done. Even more critical will be the management of the data generated and their interpretation for application purpose is very important. This is related to semantics of the data as well as efficient data handling. So a lot of large amount of number crunching or machine analytics needs to be performed to get the right insight from this data. So to conclude this lecture, utilizing sensors to gain greater visibility and real-time situational awareness is also is key. We looked at the basic definitions of IoT and some of the applications, the roadmap for Internet of Things, the ways to connect the information and collect data, thereby controlling the real world will give many applications and many use cases, and develop the application that can provide a clear business case. Number of companies or new startups can be initiated with developing right applications. Emerging technologies to address some of the IoT challenges that we have discussed. The roadmap of Internet of Things is very exciting. So there are new innovations possible. So we will look at some of these concepts in detail in the following lecture. Thank you.